In section 4 of chapter 2, we consider some special cases in which the coefficient matrix of the linear system we wish to solve has either a symmetric and perhaps a banded structure. Keep in mind when we use the term sparse matrix, we're generally talking about a matrix in which most of the elements are zero. And that does come up many times in scientific computing associated with in areas such as computational fluid dynamics, structural mechanics. In other words, sometimes where there's a geometrical structure that's involved, you typically get sparse matrices. Banded matrices also occur. In this case, the non-zeros have a particular pattern within the matrix. They're typically clustered near the main diagonal. And what you see illustrated here is a tridiagonal matrix, which has what we say a bandwidth of 3. We say as a bandwidth of 3 in terms of how many elements you would have at most in a consecutive row. And so in this case, you'd see there's 3 is the most, and this is what we would call tridiagonal. There are actually 3 diagonals. If you look, carefully, you have the main diagonal here, and then you have a super diagonal, and then you have what we call a subdiagonal. And so what we'd want to do in terms of solving a linear system is exploit the fact that those elements have that pattern, because all the elements of the other elements in the matrix are 0. And if you were to do Gauss elimination using pivot rows in order, in other words, this is a pivot, if you use the first element as a pivot element, then you would introduce non-zeros, or what we call fill-in. When you went to eliminate this element, you'd fill in other elements, and it would destroy the total structure of the matrix if you do Gauss elimination on that banded structure. So we try to find ways of exploiting that structure, and we will definitely do that with iterative methods. But it turns out with tridiagonal in particular, we can actually do LU decomposition very efficiently, because we know there's only one super diagonal and one subdiagonal. But in general, with banded matrices, you have to be careful in terms of exploiting the structure. So if we actually looked at what LU would be like for this particular matrix, again, this is a nice particular structure that you'll get, only because it's tridiagonal. But if it's tridiagonal, as we've illustrated here, and we were to look at the structure, in other words, how do the non-zeros position themselves when you do the LU decomposition, you can see what's really nice is that where you have the original trigonal matrix here, A, the L and the U, remember L is a lower triangular matrix and U is an upper triangular matrix, you get a very nice banded structure for L and U. They're actually what we would call bidiagonal matrices, because they only have 2 diagonals, the main diagonal and a subdiagonal for L, and over here for U, you have the main diagonal and a super diagonal for that. So this is a very nice structure, because most of the zeros that you had in the A are occurring in the same positions in L and U. So this is a particular case where it's very, very nice. So the natural question is, how do you exploit perhaps symmetry and banded structure when you want to solve a linear system? When you discover or you know that the coefficient matrix A has those particular properties. So the nice thing is, as I was alluding to earlier, for tridiagonal coefficient matrix, you only have to eliminate one element below each pivot element. Only one elementary operation is needed per row. And that simplifies the original LU decomp code that we had looked at for a general n by n matrix tremendously. If we look at the LU decomp3.py module that's provided in your textbook, and I will provide it on Blackboard again, so you don't need to worry about cutting and pasting or trying to retype this. It'll be provided on Blackboard for you to use. So this is a modification of the original LU decomp module, but in this case we're assuming that the matrix is tridiagonal. The previous page in the book, 61, has just the declaration of the function, but I'm just showing you the details on page 62. If you look up here very carefully where the routines are called, you've got a decomposition routine, a function, and you have a solve routine. And as indicated up here, the solver is actually going to take your decomposition that is stored in the arrays C, D, E, and with the right-hand side B, and return the solution into X, all right, which would be the solution. So again, what the difference here is that we're using an array C, D, and E to store the diagonals of the matrix. So look very carefully at this LUD comp code. You don't see A. You don't see a capital A perhaps representing a n by n array, two-dimensional array like we've done before. Or actually, in this case, you would store the lower diagonal for the tridiagonal in the array C, and then you'd store the D as the main diagonal and the E, say, the superdiagonal. Okay? So this particular code does not assume any symmetry at all. We're not using the fact that, you know, perhaps C and E might be equivalent in terms of symmetry, but this code will not assume that. We would get the length or the size of the matrix by looking at the size, how many elements are in the diagonal. That makes sense because the diagonal will have exactly how many rows or columns the matrix has. And then this is just a modification of the original Gauss elimination code we had. Here's the multipliers we're computing, but we're just working with those C and D arrays because there's a nice structure here, and we only need to do one elementary row operation per row. And then after the elimination is done, we return C, D, and E, which would have the diagonal element. The C would be the subdiagonal for the L, and then you have the diagonal matrix, and then you'd have the E matrix being the superdiagonal and the U. And then what you've got here is just a very nice solver routine that would take that, essentially the LU decomposition as provided in those diagonal elements there, and then just use the forward-back substitution like we've done before. So, so it's a very simple modification of the original LU decomp module that we had for the particular case that the matrix is tridiagonal. Very fast, very efficient. Again, the LU solver will use the B, it will update the right-hand side vector that you supply it with the solution. So if you needed to save the right-hand side vector B, you should have done that before you call this routine because it's going to overwrite it with the solution to AX equals B. Very nice module. So again, I'll provide you the LU-decomp.py module on Blackboard. Keep in mind that that right-hand side vector B will be overridden with the solution vector when you call LU-solve3. 3 just represents 3 diagonals. Just to show you a simple illustration of using this particular module, it's a very nice example, 2.11. It's on page 68 of the textbook. I'm going to show it to you. So if we look at that example on page 68, they give you a particular matrix here, illustrated here. Notice that it's in its full representation as a 5 by 5 matrix here. But clearly you'll notice a diagonal of all 2's, and you'll notice that the subdiagonal is -1's, and the superdiagonal is all -1's as well. This particular matrix is symmetric. But remember, this LU-decomp3 and LU-solve3 do not exploit any symmetry. They don't make any assumptions on the relationship between the C array for the subdiagonal and the E array for the superdiagonal. Here's your right-hand side vector B, and then as you can see at the bottom here, it's just a simple code. Here's one way you could create that diagonal into an array using NumPy. You could start off with the ones function. Say I want to generate an array of ones, and then I multiply every element by 2. So essentially, that this particular statement in Python is going to generate an array that has all 2's. It has 5, is of length 5 and has all 2's. And then you do the same thing for the C array, and then E is just going to be a copy of that, no problem. And then the right-hand side vector B, again, remember the array function from NumPy just wants a list. And so we're just going to create a list of the elements 5, -5, 4, -5, and 5. And after this fourth line, you have completely defined the matrix and the right-hand side. So the linear system now is defined completely. It's just we're exploiting structure here. A lot of this is saving storage, and it's going to save computation time. Here's the call to LU-decomp3. You're just going to update all the corresponding diagonal elements with the decomposition, and then the LU solve 3 will use the decomposition with the passing of the right-hand side B, and then what we do here is just say, solve this routine and copy and store the result into array X, and then print that solution out. And the solution is indicated below is the array 2, -1, 1, -1, 2. So let's look a little bit more at symmetry now. Like I said, we just looked at LU decomp 3 as a module that could be very efficient for exploiting the tridiagonal structure. But again, it's common to have symmetry in scientific computing. Symmetric banded matrices are very common. But we're looking at the case that the matrix is symmetric, but not necessarily positive definite. Remember, we know that we can do the Cholesky decomposition if it's positive definite, but we're looking at a little more general case here where we have symmetry and maybe we have structure in terms of bandedness, but not necessarily positive definiteness. So in this case, if we just go back to LU and say, well, if the matrix is symmetric, then we definitely know that A is equal to A transpose. That's by definition. So, but if that's the case, then a factorization of this form, A equals LU, really means we could write that as A equals L times DL transpose, where D is some diagonal matrix. So this is called the LDLT transpose. Before, remember, for Cholesky decomposition, we would write that as A equals L times L transpose. That is true when the matrix is symmetric, but it has to be positive definite. So we could just say that factorization is possible if the matrix is SPD, symmetric positive definite. What you're seeing here is definitely more general. You have to have symmetry, but you don't have to have positive definiteness. Any symmetric matrix can be factored as an LDLT transpose factorization. Okay? And what's really nice here is you could use your original ludecomp.py module that already is on Blackboard to recover the L and the D from the U factor. How would we do that? Let's look at this schematic diagram here of matching the elements of U. The idea would be that we could recover the L and the D. So again, what we're seeing is that if this is a representation of the D matrix right here, and this is a representation of L transpose. Remember, L is a lower triangular matrix, so when we transpose it, it flips it over. Assuming the Doolittle decomposition, so there's ones on the diagonal. Then if you simply multiply D times L transpose, this is the matrix you would get. So what we're saying is that you could, if you have the diagonal and L transpose, you can recover the U like we would have had before to do back substitution. And so I'm going to show you an application of doing this. It's in problem set 2.2, number 3 on page 78. You're given a 5x5 symmetric tridiagonal matrix, and you're asked to determine the L and the D so that you can write the matrix as A equals L DL transpose. So again, if it's symmetric, you can write it as L DLT transpose. If you're not exploiting symmetry, you would just do what we've normally done and say, okay, I know I could factor A equals L times U. That's always possible. Even if you had a symmetric matrix and didn't care about symmetry, you could still do that. But to save storage and to save computation, this is a factorization which is very, very useful because you really just have the L factor and a diagonal matrix that you have to produce because you can always get the U as we've indicated up above. So just looking very quickly before I show you the code that would solve the problem, let's just look at the problem specifically. This is number 3 and the problem set 2.2, page 78 in the book. So given this particular tridiagonal matrix, which we see here, and right here, here's the A, and here's a tridiagonal matrix. They ask you to determine the L and the D, assuming a Doolittle's decomposition of the symmetric matrix. So this is a symmetric matrix. We want to exploit the symmetry, and determine what the L and the D are, because again, we're assuming we're writing A as L times D times L transpose because of the symmetry. So let's look at the code that would solve this particular problem. So here's a module I called prob, actually a script file called prob 2.2_3.py. Again, I'll provide this on Blackboard under the source code link, so you'll have it as well. So this is just a code that I wrote to solve that particular problem number 3. Given that symmetric tridiagonal matrix, again, we just want to get the L and the D factors for the LDLT transpose factorization of it. I'll put a comment here, and again, I have my path to my Python 3 interpreter, so I can run this code directly on my desktop machine. I'm using NumPy, and I'm specifying the particular functions that I'm using: array, ones, zeros, the diagonal function to pull a diagonal off, which is nice, and then the dot product. It's in a module called linalg.dot. And I'm also going to use LUDComp3 because it is a tridiagonal matrix, and I'll import both of the functions that are available through it. And I'll use the operating system library because I like to clear the console screen. So I'll start off with clearing whatever is in my console window screen, and then I'll go ahead and build the diagonals. Again, we're not trying to store a 2x2 matrix. We're not trying to store an n by n matrix here. So this is a 5x5 matrix, but it's tridiagonal and it's symmetric. So in this case, what I'm doing is I've defined the diagonal right here. I took an array. I'm going to use a float type with it. Because why do I have a float type? Well, because I've specified integers on the input array. If I had just put 2 point, 5 point, 16 point, 39 point, 14 point, I wouldn't have to specify this data type. The interpreter immediately would say, oh, that's a floating point value. I know how to represent it. Just showing you some variations here. Then the subdiagonal and the superdiagonal are the same. So here, there are only 4 elements, remember, in the subdiagonal or superdiagonal when you have a trigonal matrix. And then I'm going to take E as a copy of that C array, right? Defining if we think of the C as the subdiagonal. Just for practical purposes, though, I'm going to show you what things look like. Again, this is not necessary to solve the problem, but it's just nice to have a visual. So I'm going to create a 5x5 array, zero it out, call it A, and then I'm going to do the same thing for L, and then I'm going to do the same thing for D. I just want you to see how things actually look on the screen in solving, the problem. But again, not necessary to really solve the problem to create these arrays. So what I've done here is I just want to load a dense matrix for display purposes. So I'm just going to take these elements in the diagonals, the diagonal and the super and the sub, and I'm loading them into their corresponding locations in this square matrix A. That's all I did in this for loop. And then what you see here is that I've gone ahead and taken the representation of the matrix in terms of diagonal, right down here, C, comma D, comma E, gets the factorization of that tridiagonal matrix. Again, you may say, well, wait, you didn't exploit the symmetry. No, we're not. The LUDComp3 is just to solve a trigonal matrix. You could create another version of it that specifically says that the matrix is symmetric, but we're not going to do that for right now. So we solve the problem, and then what I'm doing is loading, just for display purposes, what the final diagonal looks like. The Doolittle decomposition, remember, all the L would essentially have ones on the diagonal, and then I'm loading the corresponding elements of the L, which basically would be the multipliers in the reduction, and just so that we could see what the structure looks like. And then what I'm doing after I print the result, the original A and the D and L factors, just out of curiosity, thought, well, why don't we just multiply L times D and then multiply that times L transpose? So again, what am I doing here? I'm actually taking a dot product within a dot product. I'm going to start off and multiply L times D, and then I want to take the dot product of that result times L transpose. You get the transpose of a matrix with a really, really nice built-in numbing. rephrase that, you have this transpose function that's available that can be applied to any particular, this case matrix L, array structure, and L dot transpose would give you the L transpose matrix. Really, really nice feature that Python provides you. So then what I'm doing is I'm going to print out what L times D times L transpose is, which is, I'm saying, is an array B. Hopefully that's equivalent to A, because that's what we're just trying to show. Does the decomposition reconstruct the original matrix? We'll use the norm function provided by this linalg module just to see the error. The difference between, let's find the average difference between any element of A and B, see how small it is, and then press return to exit. So I'm just going to go ahead and run the module. Again, this is the code that I will provide on Blackboard for you. All I have to do to run it on my console, because I've provided the path to the Python interpreter in the first line of the script file. So if I run it, assuming you type it correctly, it's 2.2 underscore 3.py. And as we run it, I'll scroll back up so you can see all the results. Remember, the first thing that we did was to define the original matrix A, and then we did the LD decomposition, and then I stored them into dense arrays just so that you could see that in fact this would be, a diagonal matrix. And then we have the Doolittle form for L and the corresponding subdiagonal. So again, remember, we said this in the notes, that if it is a tridiagonal matrix, the L should only have 2 diagonals on it, and in fact it only has 2 diagonals on it, right? And then if we actually computed LDL transpose and printed it out, which we see right in this area right here. If we scroll back up and you did a little pattern matching, you could see that in fact it does fully construct the original matrix, and the error in the decomposition is 0. So this is just to check that our algorithm is working correctly. The original matrix, which is a tridiagonal matrix, did have symmetry, but we didn't really exploit it in terms of using the LU decomp through code. But we saved a lot of storage. It's a very fast decomposition in terms of the number of floating point operations, because it's just using those diagonals for all the computation, and all the other zeros in the matrix structure are totally ignored.